So let's just do a quick review to make sure, things make sense. So we started from Maxwell's equations. And then we said that basically for any antenna, or more generally for any current distribution in space, we can find the electric and magnetic fields. And the way it works is, let's say you have some antenna with some geometry. It can be 2D, 3D, whatever it is. And then at some point R in space, we want to find our electric and magnetic fields. So first we start by solving for the magnetic vector potential A. And A is found by solving basically this integral. So the integral has a constant mu over 4 pi, and then the integral is carried over a volume in space that contains the current distribution. So if you have this antenna, you want to basically make sure you integrate over the entire, shape of the antenna. And then what is the integrand? The integrand is the current distribution on the antenna. So that's the J is the basically electric current density in amps per meters squared at point R prime. What is R prime? R prime is the point on the antenna that that's the variable of the integration. We are changing R prime. Times this term, e to the minus j norm k r over r. And this, as you know, what is this? This is a spherical wave. And d cubed r is a infinitesimally small volume, basically, element. So once you solve this integral, and the assumption here is that the excitation current, basically, or how the current that we're generating on the antenna has a harmonic form. So the time, basically, variation of it is like a pure sinusoid. It has like a e to the j 2 pi ft time. And that's why there's no time in here. We're only basically doing everything over space, because the time portion, we're fixing it to be a pure harmonic. That's the assumption here. So with that, we can solve for A. So if the basically full function for A, which is a function of space and time, is the space portion, which is giving by this integral, times the time portion, which, as I said, we are assuming it's a pure harmonic, e to the j 2 pi ft. If it's not, if our current j is not varying as like harmonically, we also last time looked at a more general version of this integral, which also had t in it, and that always works. Okay, so so that's the first step. Then what do we do from A, which is the magnetic vector potential? We can find electric and magnetic fields. How do we do that? You plug your A into the Maxwell's equations, and then we showed you how you can from that find your E and H. There's no integrals anymore, so that's just you need to calculate some partial derivatives like the curls and divergences and things like that, which are typically very straightforward. But that's how you get from A to E and H. Okay, so now we have our electric and magnetic fields. Now, what we're really interested in is basically how are we radiating energy into space, or power into space? What is the distribution of electromagnetic power in the space from this antenna? Okay, because that pattern of basically radiation determines what we can see, what is the field of view, and how much echo we will get from targets at different basically angles. So the first quantity, once we have our E and H, that we usually calculate is the so-called average power flux density. So that is basically the flux of power, which is in watts per unit area, watts per meters squared. And that S, it's also called the Poynting vector, S average is equal to 1/2 the real part of the vector cross product of the electric field and the conjugate, the complex conjugate of the magnetic field H. Okay, so this is also, once we have our E and H, this is pretty straightforward to calculate, right? It's just that these are two R3 vectors. We just do the cross product and take the real part, and that's our S. Note that S is a vector, right? So it's not just how much power watts per meter is squared. There's also a direction associated with it, because that power flux, in what direction is it flowing? Okay, so S here is a vector. But the units of the amplitude of S is in watts per meters squared. Now, from there, we also said that when you look at the radiations from an antenna, there's basically different regimes that you can look at in terms of how far away you are from the antenna. In sensing, we are interested most of the time, not 100% of the time, but most of the time, especially in robotics, I can say almost always, we're interested in the so-called far field. And that's where your distance to the antenna is bigger than 2d squared over lambda, where big D is the largest dimension of your antenna. So if, for instance, it's a microstrip antenna, it would be the length of that microstrip. Or if it's a reflector antenna, like a dish, would be the diameter of that dish, basically. So that's your D divided by lambda, which is the wavelength. Okay. And again, if we plugged in some typical numbers for use cases in autonomy, like a lambda that was like a few millimeters for, say, a 77 gigahertz radar, and a D that was like also a few millimeters. And it turns out that it's far field, but physically you don't need to be that far. Usually like a few inches away is already considered far field. Why is far field important? Because certain simplifications apply. Like in the far field, our electric and magnetic fields turn out to be orthogonal to each other, and also the fields can be very well approximated by plane waves that are only traveling radially outwards with respect to the antenna. So if this is my antenna, then in the far field, basically my phase fronts of the fields can be approximated as planes, and the direction is radially outwards at every point in the space. So that's basically the simplification that happens when we do the far field approximation. And then in the far field regime, the power flux density becomes equal to the square of the magnitude of the E field at theta and phi are basically the azimuth and the elevation angles at the point that we are basically observing. So the magnitude squared divided by 2 times eta. Eta is a constant called the impedance of the medium times basically the distance is squared, right? So what this tells us is that our power flux density in the far field, there is a basically fall off that is 1 over distance is squared, right? And then the angular dependency of it is entirely determined by our E field, right? And our E field, we already know it because we found it here. So we can basically in the far field very well basically approximate our power flux density. Okay? And then this 1 over range squared drop-off should make sense, because if you're in the far field, you can kind of assume, things are you have these like big spheres for the waves, which are locally kind of flat. That's why locally it looks like a plane wave. But if you look at a much larger scale, these are kind of like very big spherical waves at the far field. And then the power is kind of like being distributed on the surface of the sphere, and the surface area of a sphere is proportional to r squared. So that's why you get the 1 over r squared drop-off in your power density. Okay. So this is okay, but usually we don't want to involve the distance when we talk about radiations. So instead of working with the power flux density, we usually work with the radiation intensity or the radiation pattern of the antenna. It's the exact same thing, except instead of looking at power per unit area, radiation intensity calculates power per unit solid angle. Okay, and then solid angle, it doesn't depend on range, right? It's the same. If you look at the cone of solid angle, it's always the same thing, no matter how far away you are from that. And then we showed that this radiation intensity or radiation pattern is simply given by the distance is squared, like norm squared of r, times the magnitude of the power flux density, magnitude of S. Okay, so in terms of the electric field, it simply becomes magnitude squared of E of theta and phi divided by 2 eta. And now the units is watts per esteradian instead of watts per meters squared. Esteradian is a unit solid angle. And this U is now just a scalar, right? There's no directionality associated with it. It's just the flow of power in a unit, basically solid angle. So from this, for instance, we can calculate total radiated power. How do we do that? If you want to find the total power that the antenna is radiating, you just assume some closed volume around your antenna, a closed surface basically, call that big sigma, and your antenna is somewhere in there. And then if we integrate the radiation pattern on that entire surface, sigma, that gives the total power that is being radiated. And you integrate over solid angles, of course. So that in watts, basically, this gives you the total power that is radiating out of that volume sigma or surface sigma. Is this clear so far? Okay, so then we started looking at, what does this U look like? What does the radiation pattern of different antennas look like? Okay, as a function of theta and phi. And this is essentially the same thing we did for sonar. In sonar, we also looked at basically what we call the beam pattern of a sonar transducer. The analog of that for radar becomes the radiation pattern of a radar antenna. Simplest one is the isotropic antenna, which basically radiates completely symmetrically in the 3D space, which means the radiation pattern U basically looks like a sphere. So it's always constant, regardless of what theta and phi is. So U of theta and phi for isotropic antenna is just U0. Okay, and then for that, if you calculate the total radiated power, you basically integrate a constant U0 over the solid angles. So you can take the U0 out of the integral, and the integral of just d omega is the total solid angle for a enclosed basically surface, which is 4 pi. Right? It's like the total solid angle of a full sphere, if you will. So the total radiated power would just be the radiation pattern U0 times 4 pi. Or the other way around, your U0, you can calculate it as the total radiated power divided by 4 pi. Now note that isotropic antennas, it's just it's a mathematically ideal case that is never physically possible. Like there's no antenna that anyone can build that would perfectly, radiate isotropically. Any antenna that you can physically build, it would have, some preferred direction in the space for its radiation. So here's like one example of a non-isotropic antenna, which has like a main lobe of radiation and a bunch of side lobes. So most of the energy would be basically radiating inside the main lobe. And then the side lobes would also have some energy. And there's some directions where you have the nulls. And in those directions, like in this direction and in that direction in space, actually no energy flows for that grayish radiation pattern that we're showing here. Okay, so isotropic antennas is one, but now, for instance, if you look at horn antennas, and last time I had one that they actually looked at, these have very directional radiation patterns. So for horn antennas, actually the axis of the horn, most of the energy would be focused towards that. One thing that is quite common when it comes to describing radiation patterns, sometimes instead of giving the full, U of theta and phi as a full function of azimuth and elevation, sometimes only the two cross sections in two orthogonal planes are given. So basically, like for this radiation pattern here, you might only be given, a cross section of it in the horizontal plane that I'm showing in red, and a cross section in the vertical plane that would be the green one. And sometimes those are called the E field and the E plane and the H plane radiation patterns, because we know in the far field E and H are orthogonal. That's just, it's not a complete description of the radiation pattern, but it's good enough for most applications. You just do two cross sections, and in 2D plots, you can describe what the radiation pattern is. But in reality, remember, to fully describe the radiation pattern, you need the full 3D, either in shape of in form of a plot or a function or you lookup table. You need as a function of theta and phi, you need the full description. Now, what determines the radiation pattern of an antenna? There's basically two factors. One is geometry. the shape of the antenna, the length of, different parts of the antenna, especially in relationship to the wavelength at which it's radiating, okay? So it's like there's that relationship between the size or the geometry of the antenna and the wavelength, and that basically determines your radiation pattern. Here's a simple one. We are looking at a dipole antenna, and a dipole antenna, remember, it's just two wires, right? It's just two straight rods or wires that are connected to some signal source that is, say, oscillating sinusoidal, or generating this sinusoidal current, and it's being fed. So this feed line or the transmission line can be a trace on a PCB or a coaxial cable. You're somehow feeding the antenna. And then we assume that the two sides have the same length, called that L/2. And then we are looking at the radiation pattern for two cases. One is where the length is equal to half of the wavelength, λ/2, and that's this case. And here, as you see, the radiation pattern looks like a donut. Just to make sure it's clear, the antenna here is aligned with the z-axis, and it's placed at the origin. Okay, so I highlighted it in red, and that's where. So this basically what it tells you is that there is no power flowing in the z direction. That's a null of your radiation pattern. So right on top of the axis or at the bottom of the axis of the antenna, you won't get any radiation. So that's one. And now if you change the length of the antenna, or alternatively, if you change the wavelength of the signal that you're feeding it, the lambda, such that L equals 1/2 lambda, 3 λ/2, the radiation pattern completely changes. Now you still have your main lobe kind of like around this, but now you add this side lobe also. So geometry, the shape of the antenna, and also the dimension of the antenna with respect to the wavelength, those two together determine the radiation pattern. Now, another antenna-related parameter that is kind of useful is the so-called directivity of the antenna. So what the directivity does is that, we have this ideal antenna, which we call the isotropic antenna, but any other antenna is non-isotropic, so it has some asymmetric radiation pattern. So directivity is basically the ratio of the radiation intensity of the antenna to that of an isotropic antenna. So it kind of tells you it's a measure of how asymmetric the radiation pattern of your antenna is. How is it calculated? Very simple. So it's called d of theta and phi, and what you do, you just divide the radiation intensity or radiation pattern of your antenna by that of a isotropic antenna. Isotropic antenna just has a constant U0 radiation density, as we know, so it's just your U divided by U0. In terms of the radiated power, remember U0 was P over 4 pi, so you can write it as 4 pi U over the total radiated power. So that's the directivity, and it's a dimensionless quantity. It just tells you. The larger the D is in a certain direction, that means a lot of power is getting radiated in that direction. Sometimes you just take the max of the directivity over all angles, all theta and phi angles, and that max basically gives you for the direction that most power is getting radiated, how much more than an isotropic antenna basically are you radiating. Here's an example. This is an overlay of two radiation patterns, so that's why it looks a little funny. But you have this sphere, which is the isotropic antenna, and then we are overlaying it with a dipole antenna, which is this donut-looking thing. So the cross-section is like you have the circle, and then you have your little donut-like thingy cross-section for the dipole antenna. And then the directivity, like the maximum directivity ends up to be being like 1.67 in the direction where your maximum power flow is for the dipole antenna. It's just a way of measuring how directive, as the term suggests, your radiation pattern of the antenna is. Okay, one more parameter is called the radiation efficiency of the antenna, which is, remember, the antennas are being fed by some circuit, right? So you feed it some electric current. So some electric power is being fed to the antenna, call that PN, but not all of that power would get radiated. Only some of it would get radiated. Some of it might get like turned into thermal losses or might get reflected back into the circuit. So radiation efficiency is basically the ratio of how much power you radiate over how much power you fed to your antenna. So here's a picture. So you have some source that is generating the electric current or the electric voltage. You have a transmission line that connects the source to the antenna. Again, this could be a trace on a PCB or coaxial cable or any means of basically feeding the signal to the antenna. So at the antenna terminals, there is some electric power P in being fed into it, but not all of it would radiate out. Only some fraction of it would become radiated power. And that fraction is called the radiation efficiency, right? So it's a number that's always less than 1, and it tells you how efficiently your antenna is converting that electric power to radiated power, basically. And then there's this notion of the antenna gain. And the antenna gain is basically the ratio of the radiation intensity of the antenna to the radiation intensity that you would have obtained if all the input power to the antenna, all of Pn, was radiated isotropically. Okay, let's make sure this makes sense. It's like, okay, you have an antenna. It has some radiation pattern U. How does that compare to an ideal antenna that has an efficiency of 1? So all the power you feed to it, it's radiating, and it's also radiating it isotropically. That ratio is called the antenna gain. It's called G of theta and phi, and a very simple expression for it. So the numerator is just U of theta, and the denominator, if you have an isotropic antenna with an efficiency of 1, its radiation intensity is just going to be P in over 4 pi, right? That's what it is. So you divide the two, you get that expression. You can also write it in terms of the directivity. It becomes equal to radiation efficiency times the directivity of your antenna, and that's the gain. This is an important one. I mean, these are all, as you see, equivalent. They are just, you know, everything from S, right, on. These are all equivalent. Like, these are just scaled versions, different scalings of the same quantities which describe how power is getting radiated out. So you have your pointing vector S, then you have your antenna radiation intensity or radiation efficiency, you have your directivity, and now you have your gain. If you have one of these, you can calculate all the others by just, you know, applying different scale factors. Historically, the one that is most of the times reported, so if you buy an antenna and you look at the data sheet, they usually give you the gain. And that's the one they report. Okay? So that's why I wanted to make sure you understand what is gain and how is it related to other you know, quantities or parameters that are defined for antennas. But usually, again, you look at any data sheet and they show you the gain of the antenna. Here's one real example of a radar system on a PCB. So this is a 77 gigahertz radar system. The antennas are microstrip antennas. And the wavelength at 77 gigahertz ends up being 3.9 millimeters. So let me zoom in on this first so we can take a closer look together. So you have the red PCB. These 4 blackish ICs you see, these are fully integrated radar transceivers. So they have all your TX circuitry and all your RX. So they generate, you know, the waveforms. They have the amplifiers, you know, on the transmit side. And then on the receive side, you know, they have your down converters and filters and ADCs and all that. Each of these has 3 transmit channels and 4 receive channels. And then on the PCB, you have the microstrip antenna. So each of these interesting looking patterns with 4, you know, squarish patches on it, each of these is an antenna. And then the antenna is being fed. You see that trace, that's a trace on the PCB that is coming from the IC. And that's one of your transmit traces. So as you see, each of these has 3 transmitters coming out and 1, 2, 3, 4 receivers coming out. So overall, because you have 4 of these ICs, you end up with a system that has 12 transmit channel, 12 transmit antennas, and all those 12 are, you know, you see them all here, 1, 2, 3, 4, 5, 6, and so on. And then you would get a total of 16 receive antennas. So there's a group of 4, a group of 4, and a group of 8 here for a total of 16. Okay, so it's a full system. And then if you just look at one of these antennas, that's the, in blue, I've shown the full pattern of it. So basically you feed it from here, that's where the signal comes in, the trace of the PCB. And then your antenna has a total length of 9.17 millimeters and a width of 1.4 millimeters. So it has a very asymmetric design. In one axis it's pretty long, right? And in the other axis it's pretty skinny. That's how the antenna is. And then the gain of this antenna, which is also, you can think of it as a radiation pattern, is shown here. Here we see the two cross sections. So these are from the data sheet of actually this radar that they showed us. Let's zoom in. So there's two plots. The red is like the horizontal cross section, or the H-plane cross section of the gain, and the purplish is the vertical cross section, or the E-plane. Basically cross section of the gain. And here on the right you see the full 3D plot of the surface of what G of theta and phi looks like. Now here's something very, very interesting. So let's look at this. If you compare the H-plane, again, H-plane is the horizontal cross section of the gain, and the purple E is the vertical cross section. You would see that the gain it has a much wider gain pattern in the horizontal direction, right? So it goes from like minus 60 degrees to 60 degrees, and then only after that the gain starts dropping in the horizontal plane, right? In the vertical plane, it's pretty narrow, right? It's only, I don't know, maybe like plus minus like 7 or 8 degrees or maybe 10 degrees, and then very quickly your gain drops, right? So your radiation pattern is very narrow in vertical and very broad in horizontal, okay? And that's a very important, basically, design decision that the engineers who designed this antenna basically made. And why is that? So this specific radar is a radar designed for automotive applications. So it is designed as a reference design to be mounted on cars, okay, for automotive applications like self-driving cars and things like that. So the environment that these radar is going to be used at, what do you want to sense? So it's a car on the road. You're not interested in things in the sky. And also below you, there is the road. You're not interested in, things that are under the surface of the road, right? So that's why you want to focus most of your energy vertically in a very narrow beam. So you only see, cars and buildings and things around you, around the horizon. But horizontally, you want a very wide beam pattern, right? We want to be able to see things for as wide as possible. Like ideally, they would have loved to have a full 180 degrees, but that's not physically possible. So they got close to it, like 120 degrees or so. So that was a design. So it's not just, it just randomly happened to have this radiation pattern. People thought about, okay, what is the use case of this antenna? What are we going to need to sense? And then they designed a geometry that gives them a radiation pattern that is desirable. And also from the geometry, it should make sense, because you see horizontally, the antenna has a very small aperture. And if you remember from the discussion in sonar, small aperture size means wide radiation, right? So horizontally, it's a small antenna, right? So you get wide radiation horizontally, and vertically it's a very long antenna, right? It has a big, there's almost like a factor of 5 difference in the vertical dimension and the horizontal dimension. So vertically it has a big aperture, which means you get a narrow radiation pattern vertically, okay? So I hope this makes sense, but also I think at this point, you should feel confident that, if I just gave you this antenna geometry and the wavelength, you should be able to, do the full analysis and get to the point where you can, fully plot the gain pattern of the antenna. How do you do that? Again, everything that's on the board. You start from the antenna geometry. You find your A. From the A, you find electric and magnetic fields, E and H. From E and H, you find your S. And then from the S, you can find U and ultimately the gain. Of course, you wouldn't do any of this manually. There's like software tools, or you write code yourself, but the process should be hopefully pretty clear for you. Any questions? Yes.
The calling the vertical plane to be H and the horizontal to be E, is that like by design or is that
I think
something?
that's kind of arbitrary. I don't think there's like real
It's not
physical.
related to the magnetic or electric field, right?
Let me think about that. There might be actually some physical significance to it. Like, for there's no, like, you could change the names and nothing would change, right? Like everything would work out. But why do they call the horizontal H and the vertical E? Is there like, does it have something to do with the polarization of the fields coming out of the antenna? Maybe. I have to think about that. Yeah. I'll get back to you on that. Okay. So the last thing about antennas, so everything we talked about so far was about antennas as transmitters, right? We were just talking about, the radiation pattern and, how the power is distributed. But antennas also can act as receivers, right? And there's one important parameter that captures that effectiveness of the antenna as a receiver, and that is called the effective area of the antenna. So what the effective area describes is basically how well the antenna is going to capture the power in a received echo. Okay? And the way that is characterized is by this parameter, effective area, which is the ratio of the power that the antenna will deliver to the receiver circuitry at its terminals, call that PS. Okay, so that's the power. Again, this antenna is now acting as a receiver. So the power that it will deliver to the receiver circuitry divided by the power flux density of the wave that is incident on the antenna, the echo wave that hits the antenna that's carrying some power flux density. So that ratio of how much power it will deliver to the flux density that is incident on it, and it will have the units of area, meters squared, because your numerator is power in watts, the denominator is watts per square meters, so you end up with a quantity that is in units of square meters, and that's the effective area of the antenna. Now, it turns out that if the echo is coming from a target that is in the far field, there's a very simple relationship between the effective area of the antenna and the gain of the antenna, and that's given by this formula here. So if your target is at the far field, basically the simplifying assumption is that the echo that's getting to the antenna is plane waves. Because we're so far away from the target, we can approximate it by plane waves. And then your effective area would be given by wavelength squared divided by 4 pi times the gain pattern of the antenna. So it depends on the direction that the echo is coming from. You don't have a constant effective area. It's a function of theta and phi, because you don't have, except if your antenna was isotropic, where G wouldn't depend on theta and phi, but for every physical antenna, your power capturing efficiency depends on the angle of incidence of the return echo. Okay. So I think this kind of is everything that like we finished the discussion about the antennas. Now we know, how they operate, both as transmitters and receivers, and how can you calculate basically different important physical parameters associated with antennas. Now we're going to use all this, and hopefully at this point I can convince you that we didn't do here physics just for the fun of physics or for the pain of physics, but this is really useful for sensing. So we are going to use all this and do something very useful, which is basically find that what is the maximum theoretical range that a radar can sense, basically, for a given set of parameters like transmit power and receive power and gain of the antenna and wavelength and so on and so forth. How far can you see with a radar? And that is the idea behind the radar range equation. It's a very simple calculation. So what we're going to assume is we're working with a monostatic radar. What monostatic radar means that the transmit antenna and the receive antenna are placed almost at the same place. They're almost co-located. They're very close to each other. Okay, so that's one assumption we're going to make. It's a monostatic, or it could be even the same antenna. It's just one antenna acting as both receive and a transmit. Antenna is at location R prime. There is a target at location R, and the target bearing or DOA angle, call that theta target and phi target. And here always the assumption is that targets that are far away would scatter all the power that's incident on them isotropically. Okay, so we assume that it's kind of like the small target approximation. Okay, so here's kind of like a picture. You have your radar antenna. Of course, this is not a radar for autonomy, but the picture I thought was cool to show something different. So here's your radar antenna. It has some radiation pattern, right, or a gain pattern, and then there is some target at location R. And then once we hit the target echoes are going to basically be distributed isotropically, or it's actually like spherical waves that the target echoes back. And those spherical waves, because the target is so far away, by the time they reach back the receive antenna, they're kind of approximated as plane waves. That's basically the setup of the problem that we're trying to solve. So the first thing we can calculate is what is the radiation power density that hits the target. Okay, that's very easy, right? It's called that W incident, WI for incident. That's just the magnitude of the Poynting vector at the target location. By definition, that's how much power or the power density will hit the target. And as we know, that's just given by U, the radiation pattern, at angle theta t phi t, divided by r squared. R is the distance between the target and the radar. Okay, we can also write it in terms of the gain of the antenna. Again, I'm just reusing everything we derived before. There's no new physics here. I'm just plugging things in to do something useful with it. So in terms of the gain, we can write it as g of theta t phi t times the ptx. Ptx is the total transmit power that we put into the waveform, divided by 4 pi r squared. So this has units of watts per meters squared, and it's the power density that is hitting the target, which is at a range r. Okay, now the target is going to echo back some of this power, not all of it, but some of it is going to get echoed back. And the amount of power that is getting echoed back, that PS, is some constant sigma times the incident power density. So this PS now has units of watts. It's the total power that the target echoes back. And this sigma is called the target radar cross-section, or RCS. It's a very famous term in radar. And it has units of area, meters squared. And it effectively tells you how much power the target will echo back. It's kind of like the RF reflectivity of the target, if you will, but it has the units of area because it needs to give us the total power in watts once multiplied by the power density that's incident on the target. So for example, there's tables that or curves that gives you RCSs of different types of targets at different wavelengths. It depends on three things basically that determine the RCS. There is the size of the target, of course, how big they are, the material that they're made of, like metallic, for instance, targets typically have larger cross sections, and the wavelength at which we are operating. So it's a function of three things. Example, like an adult male has on average has a RCS of 1 squared meters in the K-band, and K-band is like the 77 gigahertz frequency that these radars operate at. Okay, so far we have calculated total power that the target is going to echo back. From that, if we assume that total power PS is radiated back isotropically, again, it's kind of like in spherical waves, it's coming back towards us. What is the power density received by the antenna? So at the antenna, how much power do we receive? It's the total power that the target radiates back divided by 4 pi r squared. Why 4 pi r squared? Because 4 pi r squared is the area of a sphere with a radius r. And if we assume the power is radiated isotropically, it means we get just a constant power density on the surface of the sphere. So back at the receiver, so this is received power density from the target is just PS over 4 pi r squared. Plug everything in, we get this expression. It's the transmit power times the gain times the target cross-section divided by 4 pi r squared r to the fourth. And this now has units of watts per meter squared. That's the power density. We have one more thing to calculate. Okay, this is the incident power density, how much power would the antenna actually deliver to our receiver circuitry? And that, as we know by definition, so the power delivered to the received electronics is just the antenna effective area times the incident power density. So plug in the expression for A effective and make that plane wave approximation for the echo that's come back to us. We end up with this expression, which is the transmit power times the square. We now have the square of the gain times lambda squared times the radar cross-section of the target divided by 4 pi cubed times r to the fourth. And this in watts is now the total power that we have in the receiver electronics. So this is the signal that then we need to use to do sensing with, the power of the signal that we use. There's one more thing we should include in this. So nowhere in our analysis here we factored in losses. We know there's losses. There's losses, propagation losses in air. There's also losses in the electronics and other parts of the system. So we also should include that to do a full analysis. And we are going to lump in all the sources of losses into just one loss parameter, called that L. And that's just one number, less than 1, which kind of factors in all the losses that we have throughout the system. And this is then the final expression for the received power on the radar electronics. So again, it's like transmitted power times the square of the gain times lambda squared times cross-section of the target times losses divided by 4 pi cubed r to the fourth. Okay, now if you're interested, say we're interested in, okay, how far can we see with this radar? What is the maximum R? Fix everything else. What is the maximum range that we can sense? So if you solve for R, this is what you get. So R would become like this expression, which has the transmit power in the numerator, the receive power in the denominator, and everything else to the power of 1/4. One thing to note, this is not an algorithm for doing ranging, right? This is just an analysis of, the trade-offs in the system and the sensitivity, and, to establish an upper bound on how far we can see. This analysis is helpful. So to get something very actionable out of this, say for a given radar system, if you know what is the minimum received power that the radar can detect, right? Based on the noise level and the algorithms and everything, you might know what is the minimum PRX that you can work with for sensing. If you plug that in, and everything else would also be known. So your transmit power, say you decide on it and you know it. The gain of your antenna, you know your antenna geometry, so you can plug that in. Lambda, that's your operational wavelength. You can assume some target cross-section. So let's say I want to see how far I can see a human with a radar cross-section of 1 square meters. You also plug in your losses, and that would give you basically the maximum range for that choice of target and wavelength and gain and power and everything. And that's why it's called the radar range equation. So just to summarize, if you know the minimum power that your radar can detect, it's basically the sensitivity of your radar, and then you can plug that plus everything else into this expression, it can tell you the maximum range, theoretical maximum range that you can sense with that radar with that choice of parameters. Again, it's like an upper bound. It doesn't guarantee that you would see always up to that range for that choice of target and angle and everything else. It sort of like establishes an upper bound. You can never go above this, basically. Maybe you can get close to it with good DSP and everything else. Another thing that is kind of interesting in here is that this power of 1/4 makes it really tricky to increase range by just increasing power. Because, for instance, sometimes you might think, oh, if I want to see further, I'll just send out more power, right? Send out more power, I can see further out. Well, yes, but not by as much as you would think, because the power is raised to the power of 1/4. So if you double the power, for instance, you're only going to increase your R maximum range by 19%. So increasing power is not a very effective way or an efficient way of increasing the maximum range of your radar. Okay, any questions? All right, so hopefully at this point, by seeing this, it kind of justifies that all the things, physics that we did, especially to see how you find the gain of an antenna from, the geometry and wavelength and other parameters, and all the physics that we did, they're actually useful for sensing. Because, for instance, you can do an analysis like this and estimate what is the maximum range that a radar can see. Okay. So I think this is basically all the physics that we needed to know to be able to analyze and understand radars at a system level. So now we're going to start looking at radar systems and talk about signal processing algorithms for sensing. So again, here the physics would be very useful for us because we're going to use the physics to build a very realistic signal model, and then we use that signal model to develop our DSP algorithms. So starting with basically the radar system block diagram. This is kind of like a generic block diagram of a radar system. It should look very familiar. The elements of it should be the same things we saw, for instance, in sonar or in GPS also. So you have some waveform generator always, and call that waveform S of t. And then you have a so-called local oscillator. So that basically generates a carrier frequency for you, which is the center frequency of your radar. So just some pure sine wave. It could be at whatever the operational frequency of your radar is, say 24 gigahertz or 77 gigahertz or something. And then you upconvert your waveform to the carrier frequency. You pass that through an amplifier, and that gives you your transmitted signal, basically ST, which is the gain of the amplifier times the waveform that you generated times the carrier. Okay, and that goes to an antenna. This interesting looking device here called a circulator, it's basically like a 3-port device. I intentionally put it there because not every system uses it. Actually, many radars don't use it, but I wanted you to see it once because some radars do use it. And it's a 3-port device. The way it works is that it's kind of like a directional coupler. So if you feed it a signal in port 1, pretty much all of it goes to port 2. If you feed it a signal in port 2, pretty much all of it goes to port 3. And if you feed it a signal in port 3, all of it goes to port 1. So it's exactly like a circulator. So then the way it operates here is it can basically separate out the transmitted and the received signal. In the transmit path, all the signal goes from 1 to 2, and that's the power you radiate out. And then when you receive an echo, that if you use the same antenna, if it's like a monostatic radar using the same antenna, all the signal is going into port 2 and then out of port 3 and then goes into your receiver chain, which has its own amplifier. And as usual, our received signal SR is just an attenuated and delayed version of the transmitted signal ST times this term, which is the Doppler shift, and we're going to talk a lot more about it. But this e to the j pi J2 pi FDT. FD is the Doppler shift frequency that we're going to talk about. But what happens then is you amplify it through a low noise amplifier, and then you have your down converter block, which basically takes your receive signal and either the local oscillator or the modulated local oscillator, and it gives you some IF signal. You filter that, you digitize that through the ADC, and then the rest, or pretty much all the magic, happens in DSP for radars, as we'll see. So we're going to spend a lot of time talking about this block. But that's basically, at a high level, the block diagram. It's, different systems, there's variations of it. So some systems don't have a circulator. They use separate transmit-receive antennas. Some systems, as we'll see, use multiple transmit, multiple receive antennas. Some systems don't use, like older ones don't use like ADCs. They somehow have analog circuitry for doing ranging and so on and so forth. But this generally captures the essence of what a radar system block diagram should look like. Okay, let's do a bit of taxonomy on radars, just like we did for sonar. So in terms of the waveforms that we transmit, exactly like sonar, there's two classes of radar. One is the pulse radar, and this is the exact analog of pulse echo sonar. What it does, it's also called pulse Doppler radar or pulse echo radar. So it transmits short pulses, waveforms, and then the transmit is for the most part silent and just hearing for the echoes coming back. And there's many different types of pulses used in these systems. and simple ones, more advanced ones. And to do ranging, they either do simple thresholding or match filtering, exactly like sonar, right? We covered this in detail when we were talking in sonar. These also can do velocity estimation by measuring that Doppler shift, and we'll talk more about this. And the direction of arrival estimation, they either have antennas with very narrow gain patterns, very directional antennas, and then they physically scan the antenna to do directional arrival. So basically there the assumption is whatever angle the antenna is pointing to, I'm only sensing in that direction because it's a very narrow beam. And to sense in a different direction, I move physically my antenna. So, for instance, on the airports, if you've seen these rotating, parabolic antennas, those are doing, physical scanning to determine direction of arrival. Or they can also do it in signal processing using some idea called beamforming. We'll talk about that also later. Then you have your CW, or continuous wave radar. This is kind of the analog of the CTFM sonar. And the waveforms here, well, first they continuously transmit, right? They're never silent. They're just over and over sending the waveforms without stopping. And then the waveforms are either frequency or phase modulated. If they're frequency modulated, it's called the FMCW radar. Frequency modulated continuous wave, and then if it's phase modulated, it's called a PMCW, or phase modulated CW radar. Overall, they have better properties than pulse radar. So pulse radar pretty much is not used for robotics. It's used in other applications like military aviation and so on. Robotics pretty much always we use continuous wave radar. What's good about them is that they have, better properties like better resolution, smaller size, no moving parts and things like that, the CW radar, but they need more advanced DSP. So the complexity basically shifts to the digital domain in DSP for the CW radar. But that's okay, because these days we have very capable compute platforms always for these robots, so we can handle complex DSP. FMCW radar, basically, it's exactly like CTFM sonar. So it sends these linear frequency chirps and uses those for ranging. PMCW, it operates exactly like the GPS. So it uses PRN codes to do ranging based on correlations. So both of these you kind of have seen before. You know how they're going to operate. But again, as usual, the devil is in the details. So we'll see there's details specific to radar, which makes the DSP very different, say, from sonar or GPS. And they can also estimate velocity based on the Doppler shift and the direction of arrival. Again, they can do physical scanning, but in robotics, usually the DOA is also done via a technique called digital beamforming in DSP, and we'll talk about digital beamforming a lot. So that's the two types in terms of the waveforms. And here's a high-level picture showing you, what these waveforms look like. Pulse radar, again, it sends these short pulses at some pulse repetition rate, and for the most part, it's not transmitting anything. Then you have your FMCW radar, which sends these frequency chirps, right? It ramps the frequency linearly, and then it repeats, sends another one and another one continuously. And then here's a PMCW radar with binary phase modulation. And this one is taking the carrier, and it's doing a BPSK binary phase modulation of the carrier phase with say a PRN code that you're very familiar with. So it's basically multiplying the carrier by these like +1s and -1s, which are basically the PRN code. And that's the phase modulation that it applies. So this is basically one code word then. And then it sends it again and again and again and uses correlations to do ranging. Okay. Now there's another way you can basically categorize radars, and that's in terms of the number of antennas that they use. So you can have systems which are called single input, single output, or SISO systems, and they just have a single TX antenna and a single RX antenna. The only way such systems, the only way they can do direction of arrival estimation is by physically scanning the antenna. There's no other way. If you only have a single TX, single RX, there's nothing you can do when it comes to direction of arrival estimation. There's nothing you can do in DSP. Your only hope is to use very directional antennas and physically scan them. And again, an example is like the airport surveillance radars or ASRs. They have these parabolic antennas that they rotate, and these are very directional. So with just a single antenna, they can also do direction of arrival estimation, which is the angle the antenna is pointing to. Then you have MIMO systems, or multiple input, multiple output. And this is what we'll study in detail, and these have multiple TXs, multiple RXs, and they can use that to do DOA estimation without any physical scanning. So you can do that purely in DSP. They can also work with any kind of antennas. So the antennas don't need to be very directional. So they can, the antennas can be almost isotropic, for instance, in the MIMO systems. And an example is, again, like the automotive radar we looked at a few slides back. That was a MIMO system. It had 12 transmitters and 16 receivers. Lastly, there is a classification of radars in terms of the antenna configuration or placement. Again, I told you about monostatic. That's the radar where the TX-RX antennas are either the same or they're co-located very closely. And then you can have bistatic radars when your transmit and receive antennas are quite separated. OK, so these are like, we did like the full taxonomy. There was like pulse radar, continuous wave radar, single input, single output, multi-input, multi-output, and also monostatic, bistatic. Which of these are most useful for autonomy applications? And it turns out that the MIMO radars, either FMCW or PMCW, are the ones that are most basically best fit for robotic autonomy. Why? Because they can offer very high range. They can offer very high direction of arrival or angular resolution. They typically can have very small form factors, especially the ones at higher frequencies, can have small form factors. They don't require any moving parts. They are low power consumption. And you can, especially if you use these microstrip antennas, you can integrate the entire radar system in a single PCB, like the one you saw last time in class, and that makes them, very desirable for robotic applications. Now, between FMCW and PMCW, today, almost like 99% of radar systems that are commercially available are FMCW systems. There's already integrated transceivers available, and they're shipping in large volumes. PMCW, I really personally like the idea. I think it's a better architecture, but for practical reasons, today these systems tend to be more costly to manufacture, and because of that, most manufacturers picked up basically FMCW as a technology to focus on. I'm sure in a few years you would see more and more PMCW systems, but today there's not that many of them. There's one company I know of in Texas called Under that builds basically PMCW systems, and they don't sell them to general public. They just have exclusive contracts with some customers. But for FMCW, there's many companies, and you can buy either full systems from them or just transceivers and design your own antennas. So because of that, we will focus mostly on FMCW. We will talk about PMCW radar. We won't drop it, but not in as much depth. Although the slides will cover it in full depth, but we wouldn't in class go through it all because it's not as relevant today. In a few years, it might change. Now, what type of performance we can get from these radar systems? And these numbers here, these are state-of-the-art numbers, typical, but specific systems are going to be different. But you can get ranges of several hundred meters, for instance, especially at 77 gigahertz, with a resolution of few tens of centimeters. So good resolution, very high range. Now, some systems claim more than this. I've seen systems that claim up to like 800 meters range for robotics. Field of views that are can be pretty wide, like horizontally 150 degrees, vertically 50 degrees, with the angular resolution of some sub 1 degree is these days achievable with good DSP. And then they can sense very high velocities up to like plus minus 90 miles per hour with a velocity resolution of half a mile per hour, measurement rates of few tens of hertz, and they are pretty low power consumption, like in a few tens of watts. Again, there's lots of trade-offs involved, so you usually cannot hit all these numbers simultaneously. You would have to pick and choose according to your application. For instance, if you require very long range, you might need to give up on the maximum velocity that you can sense. Or if you need very high velocity resolution, you might need to give up on your range resolution. We'll study all these trade-offs. So it's not like all of these simultaneously are met, but these are kind of, the boundaries of what these systems can do. Again, these numbers are very specific to MIMO FMCW radar systems used in robotic applications. In other applications, people like in defense, people can see hundreds of miles with their radars, right? But there's no free lunch. Like something is going to give to enable that long range, basically. But for robotics, the state of the art today, these numbers are achievable. Any questions? Okay, so here's one example of again, we're talking about like FMCW systems. These days are commercially available. So you can go online today and buy this chip from TI called AWR2243. It's a fully integrated 3x4 MIMO FMCW radar, 3 transmit, 4 receivers. It can operate in the K-band from 76 to 81 gigahertz, and this is the full system block diagram. That slide with the red PCB that I showed you, where we studied the antennas, the chips, the transceivers were these AWR2243s there. And here, we now should be able to understand most of what's shown in this block diagram. Let's trace it together. So it has a ramp generator. So this is going to generate those frequency chirps. That's the part of the circuit that does that. And then that is being fed into a frequency synthesizer. So that's like the local oscillator. First, they do it at 20 gigahertz. Okay? And then this is being fed into a frequency multiplier times 4. So that's how they can get up to 80, 81 gigahertz. They basically quadruple the frequency after modulating with chirps. So what comes out of this is basically our ST, right, which is ST of t, which is the waveform that is modulated with a carrier frequency of up to 81 gigahertz. They have phase control if you want to do like active phase control. We'll talk about this, but we didn't include this block in our block diagram. And then it goes into a power amplifier, and out comes a RF signal ready to be fed to your transmitter antennas. Antennas are outside the chip, so you have to make them on a PCB or in a different way. And then on the receive side, you have your low noise amplifier, you have your down converter, and then here's basically a low pass filter, and then it goes into an ADC. So it's exactly the same block diagram that we looked at together. So to build a radar system with this, basically all you need to do is basically hook up some antennas to it, which could be microstrip antennas on a PCB, and also this doesn't do the DSP for you, so you get ADC output interface, so your raw signal out of the ADC, the digitized signal comes out, and then you have to feed it to your own DSP block, which can be a computer or a FPGA or some other microcontroller or something that can do digital signal processing for you. But that's all you need to do to build a full radar system. You buy the chip, you integrate it. I mean, of course, you have to like feed it power and the usual stuff for the electronic to work, like a crystal oscillator and power and this and that. But at a system level, really all it needs is antennas and DSP. Everything else is integrated in this tiny, few millimeter by few millimeter chip for you that costs a few tens of dollars. Really, really cheap. And that's why FMCW is so dominant. PMCW is not at this maturity level mainly because of cost reasons, basically. The cost of the requirements of PMCW systems, specifically the ADCs, need to be very high sampling rate, like gigasamples per second, which makes them expensive to make with the processes today. I'm sure in a few years that's going to change, and hopefully in 10, 15 years we can have chips like this that do PMCW also. Okay, so we're going to start with looking at FMCW radar DSP, and specifically how you can estimate range and velocity in FMCW systems. And then we'll do the same for PMCW. But again, remember, FMCW, we're going to go full depth, like no stones unturned, like we're going to do it, in painful detail. PMCW, we wouldn't go as much in depth. Okay, so here's our system block diagram specific to FMCW systems. Most of it is the same as the general block diagram, but a few differences. Here, our waveforms are these linear frequency chirps that we had seen in sonar, up-converted, and then FMCW systems, because these are CW systems, you can reuse the same antenna for transmit and receive. So they typically use a separate transmit antenna and a separate receive antenna. So on the transmit side, this is the signal we transmit. It's the gain of the amplifier times the chirp signal times the carrier. And at the receive, we receive SR of T, which is attenuation times the transmitted waveform that is delayed by the round-trip time of flight tau times this Doppler shift term, which we'll see where it is coming from. You feed it through the amplifier and through the down converter. Down converter, exactly like the case of sonar, is being fed by the receive signal, and not the pure LO, but the full, full modulated transmitted chirp. So the other input to the down converter is ST times e to the j 2 pi FCT. This is exactly the same as sonar. And then we get this IF frequency signal out. Hopefully, the hope is that this signal would have some frequency delta F, which is proportional to the round trip time of flight tau. So if we estimate the frequency of this signal, from that we get the round trip time of flight, and then from the time of flight we can estimate range, like sonar, right? That's the hope. But in practice, how it's done, we filter that, we digitize it through the ADC, we get the digitized version, and then we do it in digital signal processing. First thing we should talk about is, what is this Doppler thing that is different? This is something that we didn't consider in sonar, but here we're talking about it. So let's see where this Doppler effect is coming from. To study that, we can abstract out the details of the waveform. So let's assume there's no actual chirp modulation or or PRN codes or whatever. Let's assume the radar is just transmitting a unmodulated carrier. Okay, so the signal that the radar is transmitting is just a pure sine wave, e to the j 2 pi FCT. Okay, and that's the radar transmitter. It's hitting some target, and then some echo is coming back to the radar. Okay, so what we receive, as usual, is some attenuation factor alpha times the delayed version of what we transmit by the round trip time of flight. And if you plug in the tau, the received signal is given by this expression, alpha e to the j 2 pi fc t minus this 2r over c. That's our tau, where r is the range. So 2 times r is the round trip distance, and then 2r over the speed of light is the round trip delay, which is tau. Okay. Now, what changes is that if the radar or the target or both of them are moving, then what happens is that this r changes with time. It's not a constant anymore. So it becomes r of t if there's movement involved, right? So in that case, the signal that you receive is going to be given by this expression. You still have alpha e to the j 2 pi fct, that doesn't change, but now you have this time varying phase term phi of t, which is exactly coming from the fact that this term is now time varying. Instead of 2r over c as a constant, we have 2r of t over c. So that phase term phi is minus 4 pi fc r of t over c. Now you have a time varying phase if things are moving. Okay, so what? Well, so what? Now what happens is that with that time varying phase term, if we calculate the instantaneous frequency of the signal that we receive, we are going to see that it's not just a carrier frequency. It's carrier frequency plus a shift, that is the Doppler shift. So let's do that. Again, as you know, the instantaneous frequency of the signal is just 1 over 2 pi times the derivative of its phase. What is, and here we are talking about this signal, the received signal. What is the phase? There's a 2 pi fct plus this phi ft. So take the time derivative of that. The first one just gives you fc, right? 2 pi fct ddt, you just get 2 pi fc, divide by 2 pi, it just gives you fc. That's expected, right? But now you get this additional term, minus 2 Vr over c times fc. What is Vr? Vr is the derivative of range, r dot. And we are calling it Vr because by definition, the derivative of the range is like the relative radial velocity between the radar and the target. That's r dot, right? So now if Vr is non-zero, if there's some relative radial movement between the target and the receiver, that's going to induce a shift in the frequency, in the instantaneous frequency of the signal that you receive. That's called the Doppler shift. So the Doppler shift is equal to minus 2 Vr over c times fc, and we all know the carrier frequency fc is speed of light over wavelength, so if you can also write that as a function of the wavelength. So your Doppler shift is minus 2 times the radial velocity divided by the wavelength that you're operating at, and it's in hertz. Okay, so that's where the Doppler effect comes from at the end of the day. Also, if you want, we can write Doppler shift in terms of the actual positions of the radar and the target. So if radar is at position r prime and the target is at position r, and these are vectors in R3 now, what that radial velocity is, so r now is equal to the norm of r prime minus r. So to calculate r dot becomes basically this expression here, which is little r dot minus little r prime dot, and then this dot product with r hat, which is the unit vector pointing from the radar to the target, is basically projects that r dot minus r prime dot into the radial direction, and that gives you the radial velocity basically, and that's your Doppler shift. So just to summarize, what we showed is that when there is radial movement between the radar system and the target, what you receive, there's three basically things happening. There is an attenuation, not new, we had this before, right? There is a delay by the round trip time of flight, so you get your transmitted waveform at t minus tau, and there is a Doppler shift. So that's where this e to the j 2 pi f Doppler t is coming from. So the received signal is attenuated by alpha, delayed by tau, which is the round trip time of flight, and its frequency is shifted by the Doppler shift FD. Okay? Questions? Yes.
In sonar, wouldn't this Doppler shift be a bigger factor? Like since the speed of this wave is lesser than.
You said in sonar,
Yeah.
would it be? Let me answer that in a minute, okay? Yes, so that's a very good question. I think the question is like, why didn't we talk about this in sonar, right? In sonar, we should also, and we know we have a Doppler shift because I'm sure you've experienced it when you're out on the street, there is a fire truck with a siren coming towards you, you hear that shift in the frequency of the siren, that is Doppler shift. So it does happen for acoustic waves also, but we kind of ignored it. And I'll answer that question why in a minute. But before that, let's first talk about the ranging in FMCW radar. It's exactly like sonar, right? So you transmit a chirp, that's the green one, and then you receive a chirp, that's the blue one, which is delayed and attenuated and Doppler shifted. And then if you compare the instantaneous frequency of the transmitted and the received chirp, they're going to have basically the instantaneous frequencies are going to differ by some amount, delta f, okay? And Our signal model that now we are going to work with is this. So our transmitted signal is just e to the j 2 pi fc plus little b is the slew rate, b t over 2 times t. So by that definition, then our instantaneous frequency goes from fc at time 0 to fc plus the slew rate times the big T, which is the chirp duration at time t. And then what we receive is s of st delayed by round-trip time of flight, attenuated by alpha, and Doppler shifted. Okay. Now, with this signal model, how do we estimate range and the radial velocity or the Doppler shift? That's the problem we want to solve. Let's first see what we get out of the down converter. Okay. So the down converter essentially multiplies the received signal by, or the complex conjugate of the received signal by the transmitted chirp and extracts that delta F for you, exactly as we saw in the case of sonar. So this IF signal, which is the output of the down converter, is mu is, you can ignore it. It's just a gain of the receiver amplifier. It's just a constant, okay? If you don't like it, just cross it out. Doesn't matter by any means for our analysis. But I just included it to have a complete signal model. So it takes the complex conjugate of received waveform times the transmitted waveform, and then we plug in the two signal models that we had into this. You get two complex exponentials. This first one is the conjugate of the received waveform, and the second one is the transmitted chirp. And then you simplify things. I'm going to go a couple of steps. What you get here is the time dependence of it inside the exponent is 2 pi times b tau minus the Doppler shift times t. And then you get this second term, which is a phase term. So we can write it as mu times alpha e to the j 2 pi delta ft plus phi of tau, which is our phase term. What is delta f? What is phi? So delta f has two contributions to it. There is some f sub t that depends on the target range or the round trip, basically time of flight. So this ft is your slew rate times tau, and we know that tau is 2r over c. R is the range, c is the speed of light. So this ft basically determines the range, right? And then Doppler shift is the Doppler shift, which, as we know, is proportional to the radial velocity or the time derivative of range. Okay, so here you immediately see there is a complication, right? Because we were hoping that the instantaneous frequency of the IF signal delta f would give us range, right? But now here there's a contribution from range and there's a contribution from velocity in it. There's this coupling. There's two terms that go into delta f. So if we just FFT this SIF and find a peak, would that really be range? Maybe not, right? Because range and velocity are coupled. And we need to clarify that complication. Okay, and then phi of t, this is just for now, it's a phase term. Later it becomes very important, but this is the formula for it. There's no time t dependency in it, but it depends on tau and fc and the slew rate. Okay, it's the phase of the IF signal. Okay. So, as I said, if you look at the frequency of the IF signal, what's coming out of the down converter, it has two terms in it, ft and fd for Doppler, t for target. Range depends on ft, right, by this formula, ft times c divided by 2 times the slew rate, and the radial velocity depends on the Doppler shift via this formula, negative Doppler shift times lambda over 2. Okay. Again, this is a complication because how can I decouple my VR and R if I can only measure delta f? These two are, if I can only measure one frequency, how can I decouple it? It turns out that for robotic application, this coupling is almost of no significance. Why? Because it turns out that for almost all applications you would be looking at, the Doppler shift is much, much, much smaller than ft, and you can assume this is 0 in comparison. Let's see why. Just to justify, let's say you're working with a 77 gigahertz radar. The slew rate is 30 megahertz per microsecond. And range of the target is 20 meters. And the target is moving really fast, 45 meters per second. So this is like 100 miles an hour. So it's a very fast-moving target, very close to you. So this is like a worst-case condition where you're going to get a very high Doppler shift because the velocity is very high. And you're going to get a very small ft because r is relatively small. It's just 20 meters. Okay? But even in this case, if you plug all these numbers into expressions above, you would see that ft ends up being 4 megahertz versus the Doppler shift is just 23 kilohertz. So the Doppler shift is less than 1% of f. And it's very safe to just ignore it here and say my delta f is equal to ft, which is equal to 2 slew rate times range over c. And exactly like CTFM, you can just calculate your range from the frequency of the IF signal. Now back to the question, when we were talking about CTFM, we didn't even mention Doppler shift, right? And the reason is the situation in sonar is even simpler than this. Like even in the case of radar, we see that when you look at the frequency of the IF signal, you can ignore Doppler because it's so small compared to the frequency shift you get from the range. In the case of sonar, if you look at some typical numbers, it turns out that sonar, we know inherently it's suited for applications where things are not moving fast because it's a slow sensor, right? So when you plug in the typical numbers that you have for sonar, in the case of the sonar, you would see that the Doppler shifts that you would get are sub-kilohertz. Like they're so low that it's not even worth mentioning it. We didn't even bother with it for the case of sonar, right? For the case of radar, it's important because we see right now we're looking at the frequency of the IF signal. And for frequency, we can ignore Doppler. But when we look at the phase term, that phi term that we'll look at, that has a Doppler contribution that is non-negligible. But just to summarize again, when it comes to range estimation in FMCW radar, we just, exactly like CTFM sonar, we assume that the frequency of the IF signal is equal to ft, and then we can just estimate range from that frequency by doing delta f times c over 2 times b. What if you have multiple targets? If you have many targets that are echoing at the same time, and you receive, from one chirp that you sent, you receive, say, echoes from k different targets, same thing still works because based on the superposition principle, the signal that you receive is like the sum of the echoes from all these different targets. So your IF signal would just be mu times the summation of these IF terms which have delta Fi's, which are proportional to the range of these k different targets, and each has its own phase term. Again, we'll talk about this phase term later, but the delta F's are basically the what's important for ranging. Here's in a visual manner. So if you have one antenna with a very wide radiation pattern, so this green thing is like the radiation pattern of your antenna. It's radiating a very wide angle. And in this case, we have like 3 targets that are being hit, and all 3 are echoing at the same time at ranges R1, R2, and R3. So you receive, the green is like the chirp that you send, and then you receive 3 chirps with 3 different times of flights, tau 1, tau 2, tau 3, and each induces a frequency in the IF signal called that delta F1, delta F2, and delta F3, which are proportional to the range of the 3 targets. So we can see that if we just FFT this, we should see 3 peaks at the corresponding frequencies of the 3 different signals, 3 different targets. I think this is a good place to stop, and we'll continue next time. Any questions? All right, thank you very much.